equivalent. Okay,
Okay.
and I'm recording this. You'll get a link to where you can see this by tomorrow morning.
Oh, awesome.
As far as the control panel, you don't really need that anymore. If you want to minimize that, see that orange arrow in the upper left?
This one?
Well, I can't see what you're pointing at because I
Does it
can't see
say
your screen.
Drink controls? I'll just hit the minimize.
If you click on that, it's a toggle switch. It just minimizes, it closes the panel so that it's not blocking your view of your desktop. And then if you want,
there we go.
if you want to open it, click on it again.
Okay, I think I figured that out.
It's just a toggle switch. Okay? And right now you're seeing my screen, but you're also seeing that control panel. I have my own control panel on my screen that you don't see. And I don't see your control panel. But you do see my screen. I'm minimizing my control panel now, and now my whole screen is my drawing tablet. And we're ready to have you give me problems. For tonight, can you verbalize problems? Tell me again what your subject is. Are you in algebra or?
Precalculus.
Precalc. Okay, that's right.
And I'm doing the same review that I did the other day.
Okay. That was stuff you could verbalize, right?
Yes.
Okay. Why don't you go ahead and verbalize a problem? I'll write it, and then we'll tackle it.
Okay. Find the domain of the given rational function.
Okay.
And then it's f of x is equal to x over x minus 2.
What can x not be?
2.
Is there any other value it can't be?
Negative? No.
No. 2 is it. You got it.
Okay.
You got it. But that's what domain is all about, is figuring out what x cannot be. So if the only number I can think of that it can't be is 2, then my domain is, you can write it a number of ways. X is a member of all reals except x is not equal to 2. That's one way to write it.
Okay.
Does your class use interval notation?
I believe so.
Okay, give it to me in interval notation.
Negative infinity to 2 and then 2 to infinity.
And what's the rest of it? Do I need a parentheses or a bracket here?
A parentheses.
Okay, and then I need the union, parentheses or bracket?
Parentheses.
So that's that set. That's all real numbers except 2.
Okay.
Okay. Got another function that you want to know domain on?
Yes.
Okay.
F of x is equal to x minus 3 over x squared plus 3x plus 2.
Okay. What's our restriction going to be here?
Negative 2 and negative 1.
Okay. In other words, you're going to factor the denominator into x plus 2 and x plus 1. And now you're going to say what?
Negative infinity to negative 1, union 1 to 2, union 2 to infinity.
Good. In other words, x can be anything except, did you have minus signs in front of that? I don't think you did. In other words, it's negative infinity to negative 2. Negative 2 is what makes the denominator 0. Right?
Yes.
In union with negative 2 to negative 1, in union with negative 1 to infinity. I think that's right. Is that right?
Yes.
Okay. And once again, you could also say x is a member of all reals except -2 or -1.
-1. Okay. Next one. This one's a different kind of problem.
Okay.
It's if g of x is equal to x plus 3 and f of x is equal to x squared minus 2, find the value of f of g of a plus 2.
I think we did this one the other day. If I say what is f of 3, what do?
You plug in 3 for x.
Okay. If I say f of x plus 4, what do?
You plug in x plus 4 where x is.
Okay. Let's work this from the inside out. What is g of a plus 2?
A plus 2 plus 3.
Which is a plus 5. Now, this question is what is f of a plus 5? Right?
Right.
In other words, I can substitute for g of a plus 2, which we know to be a plus 5. So now, what is f of a plus 5?
A plus 5 squared minus 2.
Yeah, that's quantity a plus 5 squared minus 2. The reason you say quantity is because otherwise I might write it like this. You said a plus 5 squared minus 2. In other words, I have to make sure that it's the quantity a plus 5 that's being squared.
Right.
Okay. These are composite functions. Whenever you have an f of g of x, or even something like this, f of g of a plus 2, it's a composite function.
Okay.
Okay.
Now finding horizontal asymptotes.
Okay.
So, f of x is over x minus 3. I mean, f of x is equal to 2x over x minus 3.
Okay. You have 3 types of rational quotients. You have one type where the denominator or the degree of the variable in the numerator is less than the degree of the variable in the denominator, something like that. Okay?
Mm-hmm.
When you have that situation, your horizontal asymptote is y equals 0, no matter what. That could be squared, that could be to the 5th. As long as the bottom has a bigger exponent than the top, the horizontal asymptote is y equals 0. Okay?
Okay.
Second situation is when they're the same. In other words, if I had a 3x to the 4th in the top, and I had a 2x to the 4th in the bottom, regardless of what else I have, it's only the highest degree polynomial that you care about. In other words, it doesn't matter. I could have a minus 17x cubed there. Doesn't affect the horizontal asymptote.
Okay, so it's just the first.
Is only the highest degree. If they're in order, it's the first one. And if they are the same exponent, the horizontal asymptote is the ratio of their coefficients.
Okay.
So the horizontal asymptote in this would be y equal 3/2. What's the horizontal asymptote in your problem?
2. Or y is equal to 2.
Y equals 2. And you're right, it is an equation of a line. So you can't just say 2. That's a point. But y equal 2 is a line. And a horizontal asymptote is a line. Yeah.
Okay. Is the horizontal asymptote always y is equal to?
Yes. In other words, by definition, a horizontal asymptote is horizontal. And that's always a y equals something. Now, there is 1/3 situation that we didn't cover.
I think I have the next problem is like that. This situation.
Go ahead.
It's f of x is equal to x squared over x plus 1.
Now, if the numerator is exactly 1 more than the denominator, like this problem, you have to divide, and whatever you get is going to be a slant asymptote. There's no horizontal. Well, when you divide these, and I mean just like this, go ahead and divide these for me. What goes here?
So x.
And then what goes here?
X squared.
X squared plus x.
Plus x.
Because in other words, I have to multiply that by both of those.
And then
Start out by only dividing that into that. But then whatever you get, you multiply by everything. And then I subtract. So I have minus x. Now do the whole process over again. X goes into minus x minus 1 time. Multiply that by both terms. I get minus x minus 1. Subtract, I get 1. So my answer is x minus 1 with a remainder of 1 divided by x plus 1. The main part without the remainder is the equation of the slant asymptote.
So the slant asymptote is just x minus 1?
Huh?
The slant asymptote is just x minus 1?
Yes. In other words, it's going to be that line right there. It's going to go through the minus 1 y-intercept, and it's going to have a slope of 1. Okay? And there would be a vertical asymptote at minus 1. So I'm looking at this picture right here. Here's my asymptotes. So I have to draw everything within this boundary here. In other words, when you're drawing hyperbolic functions, this is a hyperbolic function. You have your regular x, y grid, but then you have your vertical and horizontal or slant asymptotes, and they kind of make up their own grid. Now, usually, these things are going to look like this. In other words, I know that my curves have to fall in like that and like this, or they could be in these quadrants. In other words, it may be the curve looks like this and this.
Okay.
And which one is it? Well, pick a point. If I pick x equal 2, if I go out here, let's pick a bigger point. Let's pick x equal 10. Well, what is my function value? 10/11ths, right?
Right.
Where does that tell me? Which of these curves is correct? It's not that one. It's the second one.
Okay.
Why? Because when x is 10, I can see that I'm right here. In other words, my value is down here. It's not above that line. It's down here. It's 10/11ths. And
Okay.
the fact that I've now I know there's a point in this quadrant, what I'm calling a quadrant. That means my two curves have to be that curve. Notice that I'm asymptotic with my slant and my vertical asymptotes. And then across the way, this curve is hyperbolic, and it also is approaching both asymptotes. So what's my end behavior? As x goes to infinity, what happens to y?
It increases? Or it's positive?
It approaches that slant asymptote. In other words, as x goes in that direction, it's going to get closer and closer and closer to that slant asymptote.
It doesn't touch the slant asymptote though, right?
Now, right, it can. Here's the thing about asymptotes. The curves can never touch vertical asymptotes, but they can cross both horizontal and slant asymptotes.
Okay.
In other words, you could have a function like this. Let's say I had a vertical asymptote there, had a horizontal asymptote there, and my graph might look like this, hyperbolic in nature, but on the other side it might actually cross over and come back towards the asymptote. The only thing we know for sure is that as we go to negative infinity, we're going to approach this horizontal asymptote. But it can go through the asymptote like it did right there. I mean, it doesn't always, but you have to kind of determine. In other words, I know that that has a horizontal asymptote of 1. And a vertical asymptote of -1.
Right.
This does not have a slant asymptote, just a horizontal and a vertical. And I don't know whether the curve touches the horizontal asymptote. How would I know? Just not to get sidetracked from your problems that you have to do, but let's say I have this problem right here. Let me draw it properly. I have a vertical asymptote at -1. Have a horizontal asymptote at 1, right? Because the ratio of the coefficients are 1. Now, how do I know if I'm crossing this horizontal asymptote? Is there a solution to x over x plus 1 equals 1? If there is a solution to that, then I know that at some point in the curve I must be crossing my horizontal asymptote, right?
Correct.
Okay, well if I try to solve that, I get x equals x plus 1, no solution. Now I got 0 equals 1. So that tells me that I'm never crossing the horizontal asymptote because there's no solution to that. So for this problem, this is going to look like this. In other words, my new grid is my asymptotes. I'm going to draw my hyperbola relative to my asymptotes, not my xy axis. Oh, and I may have drawn it wrong. I may have put it in the wrong quadrant. I did. Notice that when I make x equal 10, where's my point? When I go out to x equal 10, what is f of x?
10 over 11.
Which is below that line, right?
Right.
That means my curves are in the wrong quadrants. I should have drawn my curves like this. That one and this one. And erase that one and that one. In other words, the question with rational quotients is, are you in quadrants 1 and 3 or are you in quadrants 2 and 4? In this one, I'm in quadrants 2 and 4. But it wasn't obvious from looking at that, whether it was going to be 2 and 4 or 1 and 3. And the way I had to figure it out was to find a point and find out where that point, once I saw that that point was below my horizontal asymptote, then I know I'm in quadrant 4 with this curve. And if that's in 4, the other side of it's got to be in 2.
Mm-hmm.
And if you plug in a negative value for x, let's say I plug in negative 10, well, that becomes negative 10 over negative 9, which is greater than 1. So when I go to negative 10, my point better be above that asymptote, and it is.
Okay.
Okay? So if you don't know whether to put it in 1 and 3 or 2 and 4, just pick a point, plug it in for x, and figure out where your curve is. And that'll tell you.
Okay. Next is find all the possible rational roots for the equation.
Okay.
Of 2x to the third minus x squared plus 3x minus 6 is equal to 0.
Okay. Notice that we cannot group this. That's the only easy method of finding the zeros for cubics, is to group it. In order to group it, we need the ratio of that to that coefficient, in other words 1, negative 1, to be the same as the ratio between that and that coefficient. Well, that's a 2 to 1, that's a 1 to 2. So they're not the same. So I can't solve it by grouping. So the next thing that I consider is the rational factor theorem. What does the rational factor theorem say? It says that if I have a rational zero, what must be true of the numerator and what must be true of the denominator? It's called P over Q. What must P be? P has to be a factor of the constant. Q has to be a factor of that coefficient. Okay?
Okay.
So what are all the possible P's? All of them are all plus and minus. Just know that. So,
2 and 3.
well, let's
and
start with 6 and 1. And then go down. And then 2 and 3 are the only other two. So those are all my possible numerators. What are my possible denominators?
Plus or minus 1 and 2.
Now, let's figure out all possible P over Q's. And in other words, what you have to do is do all combinations. Do that combination, do that combination, and keep going. That one, you know what I'm saying?
Yes.
Okay, what's the first one?
6 Or
There's
plus or minus.
There's one possible rational factor. What's another one? Just do them in order.
3.
In other words, start with that and put it over both of these. Yeah, so plus or minus 3. And then go to the next one.
Plus or minus 2.
Well, go in an order. In other words, use an order so that you don't forget one. You don't want to randomly jump around here. You did this to this, now do this to this, now do that to that, and then that to that, and then that to that, that to that, and so forth. That's what I mean by going in a certain order.
Okay.
So the next one is 1. In other words, that to that is 1, plus or minus 1. And then we have plus or minus 1/2. And then we have plus or minus what? What's the rest of it?
3.
Same. We already got that one. We don't need to rewrite it.
3 halves.
Okay.
1, but you already have it. Or 2, plus or minus 2.
Right. So those are our 6 possible zeros. In other words, if there's a rational 0 here, and there figures to be, because we figure to have 3 solutions, right?
Right.
If we have 2 of those solutions, if one of them is imaginary, there has to be 2, because they only come in pairs, which leaves a third solution. And if solutions are irrational, they come in pairs. So it would be very difficult not to have a rational solution here. I couldn't have 2 irrational and 1 complex. I couldn't have 2 complex and 1 irrational. So I pretty much have to have a rational solution. How do we determine which one it is?
Plug it in for x.
And if it's a solution, what happens?
It equals 0.
Right. The more practical way to do it is to synthetically divide this by each of these. The advantage of doing that, as opposed to plugging it in, let's say I do it your method, and I decide to plug it in until I find one that this equation is correct. Okay? Now I've found my solution, but I don't know what the quadratic that would be remaining is. Right?
Right.
Well, if I use synthetic division instead, you do synthetic division, right?
Right.
Okay, let me erase some of this so it's not blocking my page. What's the easiest one to try to see if it's a solution?
1.
Yeah. And that's the only method I have. This is a trial and error process. Okay? And I'm going to keep doing it until I get a remainder of 0. It's the remainder of 0 that's the key. As soon as I get a remainder of 0, I'll know that that's a solution. Not only that, but I'll have the quadratic also that's left over when I divide x minus this number into this. I have a quadratic that I can then factor, and so I can find all 3 solutions. If I can just find one, I'll know what the other quadratic is. Okay, so let's do this. Do this synthetically. Just show me that you can do it. What goes here?
Bring down the 2. And then 2 right there. And then 1. And then 1 again. And do you subtract them, right?
You always add. The beauty of synthetic division is you're doing the opposite of what you do in regular long division. In regular long division, you're subtracting each time.
Okay.
But notice that in regular long division, my factor would be x minus 1. Well, if x minus 1 is the factor, 1 is the solution. And so what goes in the box is the solution.
Okay.
Okay? Well, this does not give me a 0. It's not 0. Okay? And if it's not 0, then 1 is not a solution. So what's the next easiest to try?
2.
Okay. Actually, I like to do these in a pattern also. Again, if I jump around, I'm not going to know which ones I've tried and which ones I haven't. So I'm going to try plus 1 and then minus 1. And then I'm going to try plus 2 and minus 2, and then 3, and then 6. The last ones I'm going to try are my fractions, because they're going to be harder to try. Okay? So let's try minus 1. I'll do it this time, just I can see how to do it. No 0 remainder. That's not a solution either. Let's try 2. Catch me if my math is wrong here. That's not. Minus 2. That's not. You can see that these problems can take all day.
Mm-hmm.
And they are. They're like 20-minute problems. So the one nice thing about that is you're only going to see one of them on the test. There's not enough time on the test to do more than one. And if you make one mistake, you're not going to catch it. In other words, you'd have to go all the way back to the beginning. You know what I'm saying?
Yes.
So I've tried plus or minus 1, 2, and 3. You can see that it goes pretty fast when you're using synthetic division.
Correct.
Minus 6. Okay, we're time to try the fractions. Let's try 1/2 first. 2, that is 1, that's 0, that's 0, that's 3, that's 3/2, no. Put a minus in front of it and try it. 2, minus 1, minus 2, plus 1, 4, minus 2, that's not it. Well, it must be the last one we're going to try. Must have a teacher that likes torture.
Yes.
No. It's going to be the very final one. The problem is that I might have made a mistake and I don't know it. You know what I'm saying?
Yes.
This is going to work though, I think. Let's see, minus 4 times that is plus 6. 9. No. This doesn't work either. Okay, let me think for a second here. Let me try something. So all that tells me is that I made a mistake, and rather than go back and waste your time redoing it all, I'm going to type it in here. It's going to tell me the zeros, then I'm going to know which is the zero, and I can go in and show you why it works. Okay? Let's see. This was 2x cubed minus x squared. 2x cubed minus x squared. This is an excellent program, incidentally. Plus 3x. It's just a website. It doesn't. You don't have to download anything or anything. And it's a beautiful. It's much better than a calculator. I'll show you why. First of all, it tells you what you put in, which your calculator doesn't, unless you have an Inspire. Okay?
Okay.
Now, it also gives you the zeros. If I look down here, it gives me the real zeros. Notice that I do not have a rational solution. I've got two imaginary solutions, and I have what appears to be an irrational solution. Now, I guess that changes what I said earlier. And I never have understood how, I always thought that irrational solutions came in pairs also. Because you end up, if you have a quadratic and you have an irrational solution, it comes in pairs. Because you have a plus or minus the square root of. But apparently, you can have an irrational solution that doesn't come in pairs, like this one. This is only one solution, and it appears to be irrational. And, gosh, from all the mathematics that we're looking at here, those are definitely irrational numbers. I'm not totally sure what they're doing here. This appears to be a solution by radicals, which is a really tough way to solve a cubic. They don't even teach it in high school or college. I was not taught this method in college on how to solve a cubic like that. The only way they teach you is this rational factor theorem. It's cruel and unusual that he gave you this problem.
Yeah, I'll ask him about that tomorrow.
Well, I tried 12 different possibilities to determine that none of them worked. That's an awful lot of work to not come up with a solution. You know what I'm saying?
Yes.
But I didn't make a mistake in my math, and I did verify to myself that there are no rational solutions. There must be one irrational or three irrational, or one irrational and two complex. And that's what there was one irrational and two complex. But I think you get the picture. And it's hard to see the advantage of why I use synthetic division, but if one of these was a solution, let's say one was a solution, okay? Well, what it left down here was the quadratic. In other words, let's say that this is my final. I'm trying one and it gives me this down here. The fact that that's a zero tells me that one is a solution. It also tells me that a linear factor is that. And it also tells me that the other factor is this quadratic. 2x squared plus 3x plus 4. In other words, it gives me both factors at the same time that it tells me that it's a solution. Much better than just plugging these numbers into the equation until you find it works. That will give you the same answer, but it won't give you the leftover quadratic. You'll still have to then go in and divide it. So the synthetic division eventually saves you a step. When you find the solution, you also know the quadratic. And then you can always apply the quadratic formula to solve that for the other two solutions.
Okay.
Okay? I know my pre-calc book does mention the method you suggested, though, where you substitute these in for this until you find it's an equation. But that's definitely one step slower because it doesn't give you this quadratic. Whereas
Right.
synthetic division does leave you with the quadratic. All right. Oh, this page here, just in case you were wondering, is Wolfram alpha. In fact,
All right.
if you want, here, I'll copy and paste it. Open up your GoToMeeting. And I'm going to paste that link. You see in the chat window?
Yes.
Click on that link. It'll open a browser on your computer and go to Wolfram Alpha and then save it if you like.
Oh, awesome. I'll add it to my favorites.
Yeah, it's definitely a fabulous. They call it a knowledge database. It's a lot more than just about math. You can type in there what's the population of Moscow and it'll tell you. You can type in there what's the elevation of Timbuktu and it'll tell you. So it's a knowledge database, but it's also the best calculator you'll ever see. Okay, what else you got? And now you can hit that toggle switch to close that thing back up again.
Okay. Find the partial fraction decomposition.
Oh, good. All right. Partial fractions.
Yes.
Love it. You don't see that very much. And the reason is that you never need partial fractions until you get to Calc BC. Only time you need it. When you get to Calc BC, though, you definitely need it. You need to be able to do partial fractions. So give me the fraction.
X over x squared minus 5x plus 6.
Okay, the first thing you want to do is factor it. X minus 3 times x minus 2. Now you want to remember how you added fractions. Let's add the fraction 1 over x to 1 over y. What do? I find a common denominator, right?
Correct.
So that ends up being y plus x over xy. Well, what if I started with that? That's what decomposing fractions into partial fractions is you start with it after you've already found the denominator. Well, if I started with this, I could break it up into some number over x plus some number over y. And I would discover that those numbers, a would be 1 and b would be 1. Okay? So that's what we're doing basically. So what I'm going to do with this thing is I'm going to say that this thing must be equal to some number over x minus 3 plus some number over x minus 2. Right?
Right.
Okay. Now, if I were to add those two, I would find the common denominator, and then on the top left, I would have a times x minus 2, right?
Right.
Plus b times x minus 3 all over x minus 3 times x minus 2. So now I can go back and I can say, well, if this is true, and it's equal to this, then x must be equal to a times x minus 2 plus b times x minus 3 . Now I got to solve this for b and a.
Okay.
Now, the way I solve it is by forcing this term to go to 0. How do I do that? By letting x equal 2. In other words, this has to be true for all x. No matter what x is, that equation has to be true. So I'm going to let x equal 2. Well, what happens when I let x equal 2? That term goes to 0 automatically, plus b times 2 minus 3 allows me to solve for b. I get 2 equals minus b, therefore b equals minus 2. Okay, I can go in there, plug in minus 2 for b. And now, to solve for a, I'm going to force this term to 0. Well, how do I force that term to 0? By letting x equal 3. So now I got 3 equals a times 3 minus 2. A equals 3. B equals, what did we come up with for B? Minus 2?
Negative 2, yes.
Now we know our answer. This thing, remember, it had to be equal to a over x minus 3 plus b over x minus 2. Well, a is 3, b is minus 2. So it decomposes into a was 3, b was minus 2. That's what it decomposes into. Now, we need to check it to make sure. In other words, if this is correct, then I can start from here and get back to there. Right?
Right.
Okay, well, let's check it. Our common denominator is x minus 3 times x minus 2 minus x minus 3, x minus 2. What goes here must be 3 times x minus 2, right?
Correct.
3 times x minus 2. What goes over here must be 2 times x minus 3. So far, so good?
Mm-hmm.
Do the math, distribute. On top, you end up with x. On the bottom, you end up with that.
Awesome.
And like I said, I'm almost surprised that they continue to teach this in algebra. I've had, well, you're in pre-calc, so that's why they're teaching it to you. But I'm surprised they're teaching it to you in pre-calc, mainly just because there's so much time that's going to take place between when you're going to need this. I've seen this taught in algebra, maybe even algebra 1, but definitely in algebra 2. But not very much. I would say about 1 out of 100 students that I get learn this. This only comes up outside of calculus. This comes up about once every 2 years for me. So it's interesting they're teaching it to you now. And it does get considerably more complex as the function gets more complex. Okay?
Mm.
You're just doing a half hour tonight, yeah.
Correct.
Is this the only partial fraction problem you have, or do you have another one?
I have one more.
Let's do it real quick.
Okay.
Let's hope it's not a second order one.
It's 5x
Okay.
plus 7 over x squared.
Go ahead and
plus.
we know it's going to have to be factored. Let's factor.
All right. X minus x minus 1 and x plus 2.
So
Wait, no.
So the function was x squared plus x.
Wait, no, it's x.
What is the function? X squared what?
X squared plus 2x minus 3.
All right.
So it's x plus 3 and x minus 1.
Yeah. Okay. Now, you remember what to do from here. The very first step is always pretty much the same. Go ahead and split it up into two fractions. The only thing you don't know is the numerator, right?
Mm-hmm.
In other words, it's equal to something over x minus 1 plus something else over x plus 3. Well, we don't know what it is, so we're going to label it A and B. That's step one. Now we need to solve for A and B. Well, add those two together, and what would you have?
A of x plus 3 plus B of x plus 1.
X minus 1.
Minus 1.
And all of that would be over that common denominator, right?
Correct.
In other words, x minus 1 times x plus 3. What's the next step?
Find the A.
Well, notice that I have this equals this at this point, right?
Right.
The denominators are the same.
So you can cancel them?
I can equate the numerators. That's the key step. In other words, 5x plus 7 has to equal my numerator over here. 5x plus 7 has to equal A times x plus 3 plus B times x minus 1. Okay? That has to be true. Now, we still have a bit of a problem here because I got two variables and only one equation. One would think that we wouldn't be able to solve for A or B. However, we can always come up with an x that makes that term 0, and that's going to let me solve for B. And we can always come up with an x that makes that term 0, and that's going to let us solve for A. So this is kind of a special situation which allows you to solve for A and B even though you only have one equation. The fact is this equation has to be true for all x. Doesn't matter if I put in x equal 10, this equation is going to be true. So let's come up with some special x's that make this term go to 0, allowing me to solve for B, and make this term go to 0, allowing me to solve for A. So what x's should I use?
-3 and 1.
Okay, so I'm going to use x equal -3, and now let's rewrite that equation using x equal -3. What's the left side become?
-15 plus 7.
Which is -8 equals, this whole term goes to 0, 0 plus
-4.
Well, there's only one negative sign there. It's a plus b with a coefficient of -4. So it's minus 4b, right?
Right.
You see how I got that? In other words, it's plus b times -4, which is minus 4b. So b is equal to 2.
To 2.
Okay. Now, I don't even need to use that to solve for a. I just need to find another x that makes my b term go away. What would that be?
1.
Okay. Let's rewrite this equation using an x of 1. The left side becomes 12. What's the right side?
3a.
X is 1.
Or 4a.
4a. Now I've solved for a. A equals 3. Well, if a equals 3 and b equals 2, then it's 3 over x minus 1 plus 2 over x plus 3. And there's my answer.
Okay.
Okay? It's a little tricky. If you're going to have these on a test, I would definitely recommend you try one more on your own. Try to find one and do it. Because it's a little, this is the only math problem I can think of that uses this technique, where you find an x that makes one of these variables disappear, and that way it allows you to solve the equation for the other variable. By the two variables, I mean a and b.
Okay.
Okay? But yeah, those are fun, actually. Once you know how to do them, they're fun. Still don't know why they teach it in pre-calc, because it'll be at least 2 years before you need to use it. You won't use it in Calc AB. You might use it in Calc BC or get to college and use it in Calc 3. But who's going to remember how to do it 3 years from now? So
exactly.
I think the new standard in teaching is wait until you take calculus before you teach partial fraction. And that's why I don't get very many students that have those problems.
Mm-hmm.
Okay. Audrey, you have another session scheduled for Wednesday. I will talk to you then. Now, on Wednesday, I will only text you the meeting ID number. I won't call you.
Okay.
And you should have on your desktop an icon that looks like this orange flower.
Okay.
You see it?
Yes.
Just double click that and input the meeting ID number I text you, and then we'll be in a meeting.
Okay.
So I don't need to verbally call you. I'll just text it to, as long as I have your cell number and you gave it to me. Is that in the future, probably put the cell number on here that you want me to call. Is that the right one?
Okay.
3097? No. You got it down here. That's okay. I've got you in my phone now, and I've got this number down here. So I'm fine.
Okay.
I got your phone number for the future. Audrey, have a good evening, and I will
You too.
talk to you Wednesday.
All right, see you then.